All right, so here's the kinds of problems that we're talking about with counting rules. We're going to look at two different types of counting rules and how you can come up with the total number of possibilities for a given situation. And I'll get into those two different scenarios. But first, I'll just start you with the problem. Go ahead and take a picture of this. And I want to work through this one, talk to you about how to make it work for you. Here's what's going on. So we've got this paint manufacturer. At this particular store, they only have 7 colors. They have 2 types of paint. There are 3 textures and then 2 uses for it. Okay, this is a relatively simple type of problem. There are many more possibilities than this if you were going to a store and actually buying paint, but for our purposes, it makes it kind of easy to figure out. Now, one of the reasons counting principles are important is you want to consider the number of possibilities sort of per slot. And just like I did that example just a minute ago for the heads of households playing video games, we use the same concept here. Okay. So in this case, I have 4 different categories that I'm choosing from. And in order to come up with the total number of possibilities that exist, I have to choose from each category. And then when you figure out however many possibilities there are from each category, you just have to multiply them together. Okay? That's how the counting principles work. So, how many possibilities are there for color?
7.
7. How many for type?
2.
How many for texture?
3.
How many for use?
2.
Okay. So essentially all I'm doing is filling in the number of possibilities for each slot. And then I'm going to multiply them together.
84.
Okay, so what does it give me when I multiply them out?
12.
84. Okay, so that's the most basic counting principle. And so there are 84 different paint possibilities at this particular store. Okay, again, the way you want to think about them is you have each slot that has so many possibilities, multiply them together, and that gives you the total number of possibilities. Now, one of the things that we're going to use when we look at some of our accounting principles is something called factorial. And you may or may not know what factorial is, okay? The factorial notation is when you'll see a number followed by an exclamation point. And that's what I'm going to show you on your calculator where to find that, because it'll do it for you. But I want to tell you what factorial is. Does anybody already know what it is?
Oh, I know.
Okay.
Is it when it's like each one preceding it? Something like that, right?
Okay. What about it, though? Yeah.
It's adding up.
Adding up?
Value, adding up every value, multiplying every value.
Multiplying all the values. Yes, that's correct. So, right. So you're both basically together. Okay, so for example, here are 2 examples, okay? 5 factorial means you start at 5 and you multiply all the way down to 1. 9 factorial means you start at 9 and multiply all the way down to 1. Obviously, if I was going to do this multiplication, I mean, I think you could do 5 factorial in your head or get pretty close to doing it in your head. 9 factorial in your head would not be fun, okay? Or writing all of this out would not be fun. So I'm going to show you where you can find that on your calculator and just type in 9 factorial or 5 factorial to give you the answer. So on your calculator, here's where it is, okay? On the TIs anyway.
What's the point of factoring?
I'm going to show you here in a minute. Okay, if you hit the math button, which is under the green button, and you scroll to the right to where it says probability, PRB, then it's number 4. Okay, so if you went to your normal screen and you typed 5, and then you hit the math button and scrolled over the PRB and hit 4, and then hit enter, it'll give you 5 factorial. It'll do this for you, and it is 120. Okay? Okay? Now do 9 factorial. See what that comes out as. Okay? Right? Doing that multiplication would not be fun. I want you to notice something else, and I'm going to come back to this in a minute. Notice this. Okay? What I've just underlined is 5 factorial. Okay? This 5 times 4 times 3 times 2 times 1 is 5 factorial. So I could have written 9 factorial, and later on you're going to see why I would even want to do that. I could rewrite this as 9 times 8 times 7 times 6 times 5 factorial. That is the same thing as 9 factorial. Again, when we get into some problems here in a little bit, you'll see why I might want to do that, okay? Now, general rule for factorial. Any number, n factorial, is n times 1 minus it times 2 minus it. So like if 9 was n, I'd subtract 1 for the next one. I'd subtract 2 from it for the one after that. I'd subtract 3 from it for the one after that. All the way down to 1. Okay. And then we make up 1. 0 factorial just always equals 1. We make that one up so that it doesn't, we don't ever multiply by 0. Okay, if you're in a situation where you end up with 0 factorial, just know it always equals 1. And the reason is otherwise it would make everything 0, so we leave it out. And also because n factorial ends with 1. Every factorial ends with 1. So this is the one we just sort of make up. Okay?
Right.
Let's get into our two different types of counting principles. The first one is known as a permutation. Okay? In a permutation, an arrangement of n objects in a specific order. So order matters. Okay? How many of you have a locker at school?
I don't think seniors use it.
You guys, okay, how many have had a locker at one time in your life or opened a padlock? What do they call that 3-digit thing or 3-number thing that they give you? They call it a combination. The truth is, it's not a combination.
It's a permutation.
It's a permutation.
Yeah.
The order matters, right? If you scrambled those numbers up and didn't do the first number first and you did it second, your lock's not going to open. The fact is they should be calling it a permutation, not a combination, because the order really makes a difference. Okay? Sometimes order doesn't matter, and we'll get into that in a minute. So let's start with an example here. Okay? Again, if you want to take a picture of this, you can. So yeah, 229 in your book if you want to grab it from there. Television news director wishes to use 3 news stories. All right? One story will be the lead. One's the second, one's the third. Does the order of that matter?
Oh.
Yes.
For sure. I mean, if you're trying to do a certain story, the order matters. Okay? There's 8 stories that might make it on the broadcast. Okay? They're going to choose 3 of those 8 stories. And then we want to figure out how many different ways can the news director run the show. How can the program be set up? So again, what you want to do is think of the number of slots that you are choosing. How many slots are being chosen?
8.
3. So I've got the lead. Oops. I've got the second story, and I've got the closing story. All right. How many possibilities are there for the lead?
3.
8. There's 8 stories to choose from. So I could have any of those 8 stories right there. How many for the second? Knowing that we've already chosen one for the lead. 7. So now we've chosen 2 stories. How many are left for the closing story? 6. Okay. So the number of possibilities for this particular situation is just going to be 8 times 7 times 6, which is 336. So there's 336 ways that this news director can choose a setup of 3 stories from the 8 that have already been produced. Okay? This is one way to look at it. Using permutations, I'm going to show you the formula to come up with the same number. Okay? And those of you who figured this out know that your calculator will also do it for you. However, and I'm going to say this, make sure you hear it loud and clear. You still have to write the formula out that I'm about to show you, even though your calculator will do it for you. I want to make sure you know how to use the formula. Okay? So here is the permutation formula. Go ahead and write that down. That's also on 220. So here's what's going on. You're going to choose, sometimes this is read as n choose r. You're going to have n things and you're going to choose r of them. And it's a permutation, meaning that the order matters. Okay, and it says here, permutation of n objects taking r at a time. N choose r is a lot of times the way it'll be written, or the way you'll say it. So in that particular case, okay, what was n? How many total objects were there for the previous problem? 8. There were 8 shows to choose from. How many were selected? 3. So for using the permutation formula, there n equaled 8, r equaled 3. And I want to show you how the permutation formula will still give us the same answer. In fact, sometimes it'll be easier to use the permutation formula to come up with our answer. Okay. Because essentially what I'm doing is this. Permutation of 8 things choosing 3. Or 8 choose 3. Permutation of 8 choose 3. Lots of different ways to say it. So when I go ahead and plug into this formula, so this is what I'm saying, even though the calculator will do this for you, I want it written out using the formula. So on top I get 8 factorial. On bottom I'm going to have 8 minus 3 factorial, which is just 8 factorial over 5 factorial. And here's why, when I showed you earlier about that 9 factorial was 9 times 8 times 7 times 6 times 5 factorial, I can do the same kind of thing right here. Alright? And here's what I mean. Since 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, it's really times 5 factorial. Right? Those two things are the same. Now obviously the reason I want to write it that way is because if I have 5 factorial already on the bottom, then I can just cancel these two out. Alright, and come up with the same values that I had using the counting principles. So using it as slots, 8 times 7 times 6, like I did on the previous slide, is using counting principles. Over here now I'm using the permutation formula to come up with the same answer. So you can use either or unless the directions are specific. If the directions specifically tell you, use the counting principle to come up with your solution, then you have to use slots and fill it in as 8 times 7 times 6. If the directions tell you, use the permutation formula to come up with the answer, then you've got to do it this way. Okay? Obviously I get the same answer. 8 times 7 times 6 is still eventually what I get to. But again, if you punch this into your calculator this way, it will do it for you. Okay? So there's our answer, the same answer that we got. No big deal. So go ahead and use the permutation formula to figure this one out. Use the permutation formula to figure this one out. Counting principle you can use as a check, but I want you to use the permutation formula right now and get used to that. I definitely recommend identifying n and r first. That'll make doing this problem a lot easier. So what is n in this problem?
9.
What is r? 2. Okay, so then it's just a matter of plugging in the formula and go from there, right? So here's what you should have gotten for your formula. So when it asks you to use the permutation formula, you have to write this out. Okay, from here now, we can use the same ideas that we just had. 9 times 8 times 7 factorial to get it to cancel with 7 factorial. Get those 7 factorials to cancel. So my solution is just 72. Okay? Questions on that? Alright. Let's move on to combinations. So combinations, this is why when I was saying about the padlock thing, they shouldn't be called combinations, because combinations, order does not matter. Okay? Obviously when you use a padlock, the order makes a big difference. Okay, but for a combination, mathematically the order doesn't matter. Okay? And this is where I'm going to teach you how to win the Mega Millions. In the Mega Millions, okay, the order of the numbers in which they are selected, or which you select them, or which the balls pop out of the machine, don't matter. You just have to have the numbers. Okay? Now, I'm using the example of the Mega Millions, even though right now the Powerball is higher, but the same concept exists. It's just different number of numbers, okay? First thing I want to show you, and I happened to write this one last semester when the Mega Millions was in the billions. Do you remember that, when it got up to over $1 billion?
Oh, yeah.
Yeah. Okay. So you'll see why it's hard to win. Okay. Rules. Okay. If you want to take a picture of this, you can. But here are the rules for Mega Millions. So what happens is there's two separate pools of numbers. Okay. One set has 70 numbers in it, and you pick 5 of them. The order of those numbers doesn't matter. So you have to get all 5 of those right, and then from a separate pool of numbers, that's where the, like in Powerball, they call it Powerball, comes from. I don't know what it's called in Mega Millions. But in that set, there's 25 numbers, okay? And so you have to get all 6 right. You got to get the 5 right from the 1 through 70, and then you have to get the one like Powerball right, or Mega Ball, or whatever, all right? Now, here's how this works then, all right? First of all, I want to show you what the formula for combinations is. And this is where order matters. This is the combination formula. It looks very much like the permutation formula. However, there's another extra r factorial on the bottom. So, order does not matter. For combinations, order does not matter. Okay? So this is the same idea. You have n things to choose from. You're choosing r of them. And then as a combination, what we're doing is eliminating the repeats. So for example, if I had a combination of 1, 2, 3, okay, 3, 2, 1 does not count as a different one. 2, 3, 1, 1, 3, 2, okay, 2, 1, 3. Those are all the same set of numbers for a combination. For a permutation, they would all be considered different. Right? So when the numbers are all the same, the order of them doesn't matter. That's a combination. When 1, 2, 3 means something different than 3, 2, 1, then we're talking about permutations. And the way that we eliminate the quote-unquote repeats that have all of the same number is we divide by this r factorial. Okay? Because the 5 numbers that we choose from 1 to 70, the order of those numbers doesn't matter, this is a combination. In this case, from the 70 numbers, how many do you choose? 5. You choose 5 numbers from the 70. So the first part, from the first pool of numbers, what we have is a combination of 70 choose 5. I'm choosing 5 of those numbers from 70. So in this case, when I plug them into the formula, n is 70, 5 is r. So when I plug it in the formula, it looks like this. Okay, 70 factorial on top, 70 minus 5 here, that's 65, times 5 factorial. So I want you to take this and plug this into your calculator and see what you get. You enter all of this in its own set of parentheses at the bottom. So it may be that you have to go like this when you enter it into the calculator. Okay. Since it's doing that, what I'm going to do here is I'm going to eliminate some of these numbers. And what I'm going to do is I'm going to make this 70 times 69 times 68 times 67 times 66. And then the 65 factorial is going to cancel out with it. Kind of how we did the other one. Try that now. So 12,103,014. That's how many possibilities there are in the 5 numbers that you select, which that by itself doesn't seem so bad, right? Theoretically, just for this part, there's 12 million possibilities. Okay? Now, for the last number that you draw, there's how many possibilities? There's 25. So I have to take this times 25. Because it's like those first 5 slots, the order doesn't matter, it equals this. Then the last slot times 25 is what's going to be the total number of possibilities for all Mega Millions combinations, okay? And when I multiply that, I get 302,575,350 total possibilities. So let's talk about that. Mega Millions tickets, if you buy the Power Play or whatever, it's like $3. Okay? So in order to guarantee that you, first of all, so that means that's $900 million, right? That you would, if you wanted to buy every single ticket, you would have to spend over $900 million to guarantee that you win. So when it was over $1 billion, right, you could guarantee you were going to win. Now, that being said, in order to fill out 300 million tickets, I don't know how long that takes. You have to bubble in 300 million tickets, and then you have to show up at the Publix desk with 300 million tickets and $900 million to win $100,000. Now, if you can show up to Publix with $900 million, you don't need $100 million. It's not that much, right? My point of showing you this is that while you can win, there's a reason why people don't win. There are still, even if I bought half of the tickets, let's say a third, 100 million tickets, that would cost me $300 million, okay? You would still have to fill those tickets out by hand. So the answer, why haven't I won the Mega Millions yet? Because I don't have the time to fill the tickets out, nor do I have the cash to buy the tickets. Now, are there people in this world who do? Probably. I don't know how much time it would take. If you had a business full of people that their job was to fill out the lottery tickets for you, and then they would have to process that. I don't know how long that takes. Like, let's say it takes a minute to fill out one card, right? Let's say it takes a minute. Okay.
525,600 minutes in a year.
How many?
525,600.
525,000 minutes in a year?
I think.
Okay.
Is that from that song?
There's 525,600 minutes in a year.
Oh.
So if it took you a minute, right, we're not even close to that. If you did it by yourself, it would take over 576 years. If you did a minute per ticket, you never slept, you never ate, you never went to the bathroom, right? So you'd have to have an enormous company to do that for you. Even if you had 100 people doing that at that rate, it's still 5.75 years.
A year for
Okay.
576 people to do it.
So this is why the lottery does so well. Like, the ability to get this all done is very, very difficult. Now, okay, two things to keep in mind between permutation and combination. It all has to do with whether or not the order matters. So as you enter into these problems, you have to ask yourself, does the order matter in this situation? If the order matters, then it's a permutation and you use the permutation formula. Okay? If the order does not matter, like in the Mega Millions, on
Yes.
I'm trying to think of another example.
Right,
It just escaped me. Where the numbers order doesn't matter, then it's a combination. Okay.